Okay, how's everybody doing? Remember that Wednesday we do not have class and I do not have office hours. There you go, April 10th. All right. Any questions on the homework? No, we have no questions. Instruction was great. Everybody's able to do this one? Yeah. Did you learn anything with that one?
Yeah, that was a good problem. It was great.
I made that one up myself.
You feel it's really exciting.
What? Well, I always do this when it's Miller effect and no one ever understands it. And so I'm like, well, maybe if I do a simulation problem where they have to simulate it, they'll see that it's the same. But of course, what does Miller effect neglect? The zero. Remember, the input and output at high frequencies get shorted together through the capacitor. When you go to here, you don't have that shorting, right? Okay, so over here, this one you need me to do? All right. Well, so first off, and we'll cover this today after we talk about cascodes, because cascode, if you see for the next homework assignment, the cascode amplifier, this one, everybody see that? You need to make sure you can analyze that. So I'll do the frequency response, but before I do that, if you look in the book on page where are we at here? Is that where it is? No. The summary, whole splitting summary. You see these right here? Whoops, you can't see that, can you? Okay, so you see these equations? You don't derive those every single time. Rather, what you do is you use those equations. So when you do homework problem number 2, you're going to use those equations. And I want to go through, does everybody see that here I've got R1 and GM1 and S and all that? And you see I've got C1, CC, GM2, V1, R2, CC. I'm going to do homework 2 and then we're going to compare what I get to simulations, since you already did that, right? Okay, so let's go look at homework 2. And first thing you note, in the that model, the pole splitting summary, the input R1 and GM1 don't coincide to what I have here. So what I'm going to start out doing is I'm going to Nortonize this equivalent circuit. So I'll go back and I say 1 and 75K. And how do I treat the 1 microfarad? It's a short. For open for DC, short for AC. Okay, so we'll start here, 75K and 1. So I go back and I'll draw my input, and let me make sure I do it the same way as the source here. So, and let me do it because I have phobias about your circuits knowledge. So let's draw it like this, plus minus 1 volt. And then I have a 75K. Here's the ports. Then would everybody agree that if I'm writing this as a current GM times VN, and this is my resistance R1. Let's do the easy one first. What is the R1? Well, let me ask this, even easier. When you're determining the Norton equivalent from the Thevenin circuit, tell me from your instruction, how do you go from here to here? Simple, simple. You're explaining it to someone in circuits 1. There's 2 ways of doing it. One, when you calculate the equivalent resistances, you short out all of the voltage sources and you open the current source. And then you put a meter here and you measure. So when I short this out and I put a meter there and I measure, what do I measure? 75K. Now if I'm going the other way, I open this up and I measure the impedance, the resistance between the two terminals, and what do I get? 75K. Everybody see that? So is there any questions about that? What was the other way that's a little bit more challenging? Put a short across there, measure the short circuit current, which would be 1 over 75K. Divide that into the open circuit voltage. What is the open circuit voltage here? So it ends up giving you 1 divided by 1 over 75K or 75K. Now I go back and I say, okay, well, I need the same thing for my VN. So my VN is 1 volt. If I want to make sure that I have the same open circuit voltage, what is GM then? Well, what is VN? Let's call this VN. 1. So what's GM? So when I multiply VN, which is 1, times minus 1 over 75K, I get a current of minus 1 times 75K. When I pull it backwards, I know that VOC is minus R1 times this current, which would be minus 75K times minus 1 over 75K times 1 or 1 volt. Did I lose anybody there? Make sense? So there's my GM. So I'm going to write those down. R1 equals 75K. GM, I'm just going to use, because it doesn't matter, it's AC, you can flip it around. I'm just going to say 1 over 75K. Now, you note in this problem that you have an R and a voltage source, right? For, let's see what the next homework problem is. Well, let me just pick one in the book instead of looking. If I look at the, so here is the example I basically did just a moment ago, where GM would be 1 over 100K. If I look here, though, and I ask you, here's my source voltage, why isn't there a pole associated with the input? Why don't I have a pole? Why in this calculation do I just have R1 and R2 and the 2 poles? Yeah, there's no input resistance, thus there's nothing to limit how fast I charge and discharge the input capacitance here. We all see that? There's no R. R is 0 here. So no RC time. But if I ask what is the resistance, it would be the resistance looking back here, which would be R out 1 or R out A in parallel with R out C. Everybody see that? And so we'll use this in our op-amp stuff. Any questions? Okay, I got a question. Let's go back to the pole splitting summary, and then I'll come back to one of these examples. You see the GM1 here? Which equation uses GM1? Well, wait a sec. The gain does, right? So for the overall gain, what about R1? Which one's using R1? Right there. So if I go back and I look and I say, what is R1? You see your 100K there. Okay? All right, so now let's go back to this problem, which is your homework. And then let's go to, where was it? here. All right, and so this, what is this capacitance right here? That's C sub C, that's 1 pico. And then what's the R2? Yeah, let me actually sketch this circuit just to make sure we're all, I don't want anybody not to follow. I didn't. I didn't plan right. I know, let me get what we have here, 75K, 1 pico, I think we're done. So I think I can remember that. So we have our nice little 1 volt source. We have our 75K. We have a big capacitor I'm not going to draw. And I have a little bias here. Oh, how many people are doing senior design this semester and going to the senior design banquet this semester? When is it? May 9th? I'm trying to figure out if I can go to that. All right. What's that? No, I just want to attend and meet people. I'm not introverted. I know you may think I am, but I'm not. Yeah, all right. R1 is 75K. And C1 is equal to, help me out. Let's do CC. You already told me it's 1 picofarad. What is C1? How about CGSN? Anybody agree with that? And I'm going to cheat and look at the back of the book. I guess it's not cheating. That's what it's there for. That'd be 23.3 femtobabies. And R2 is? Yeah, let's do it this way so no one puts milliohms. And then what is GM2? And then what is C2?
6.
Well, I don't really have this one, right? Because the CC is much larger and dominates. So it's basically only going to be this capacitance. C, G, D, P, which is 6 femtobabies.
So wait, so the GD capacitor is still there. It's just
Yeah, it's still there, but it's in parallel with CC, and since CC is 1 pico, that's huge compared to this. So I'm just going to say CC is 1 pico, but I could put plus CGD just to be a little bit more precise. Any questions? All right. And then the gain would be GM1 times R1 times GM2 times R2, which is at low frequencies. What's GM1 times R1? That'll give me, what is GM1 times R1? One. And then GM2 times R2 is what, 333 or something like that. So it all works out. All right, any questions about this these before we plug in the numbers? All right, so which one, what do we need to calculate here? Or actually, let me, before we do that, how would I modify this for problem 3 when there's a load capacitance? There would be a load capacitance which would add to what? C2. So if I put this here, Oh, whoops, wrong one. Does everybody agree with that? And so if it was 1 picofarad, then C2 would be basically 1 picofarad. You could say it's 1.006, but for all intents and purposes, it's 1. Any questions about these? Did anybody do it this way? Okay, and then we have F1, FZ, and that's F2, FZ. All right, those are our poles and our 0. Let's do the easy one first, which would be what?
0.
The 0. And if I go look at my nice little equations, are you sure this one was hard? Or am I just having no clue about what's hard? And FZ is GM2 over 2 pi CC. GM2 over 2 pi CC, which is 150 micro over 2 pi times 1 picofarad, which is what? Like 10, 11 megahertz, I'm guessing. Oh, you just did it. You don't need your calculator. FC, 150 over 23 megahertz.
Yes, 23 minutes.
Yay or nay?
Yeah.
So why don't we pause and see if we can see that in the frequency response? You think we'll be able to?
Yeah.
Were you able to?
Right.
What? So this is lecture 18 on April 8th. So you guys, I asked my 221 class what they thought was better if I teach 220 every semester or 221, 220, 221, 220, 221. Half of them said 220 every semester, and the other half said 220, what did I say? Half said 220 every semester, the other half said 221, 220, 221, and the other half said you shouldn't teach them at all.
Wow. Wow.
No, they didn't.
Low
You should do 220. I would have loved.
You should just teach all the engineering classes every semester.
No. Practically, seriously, would it be better if I did 220 and then?
I would have liked it if you were able to teach my 221 class.
Yeah, but then what if you took, how many, you took 220 in the spring?
I think you should always.
See, you guys are giving me like half are saying all 220 and half are.
Yeah, you teach 221 and 220 anyway.
220.
No, I've been teaching 220 every semester.
But you like trail off the end of the class.
Yeah, because I'm paranoid that they're not going to get anything in 221.
He prepared us for 221. That's why I see.
I don't want to.
Would have never survived 221.
When I said that, about half said 220, half said 220, 221, half said they didn't care. I was thinking of half man, half pig, half bear. Did anybody get that reference? Man, bear, pig. Half man, half bear, half pig. That's a that's a reference to pop culture. Hopefully you got it.
Let's go back to zero.
I have a question. Why do you say femto babies?
Because I'm bored and it gives me something to think about. All right. Yeah, gotta be different, man.
Does it have a story or is it just that's
Oh,
it?
that's it.
That's it.
Then two babies. Yeah.
All right, did I do this right?
The value of the CG.
Any questions before I do this, Sam? David, any questions?
I have a question.
Lay it on me.
I don't understand why the load is only added to C.
Because it's added to C2. So this is node. If I go back here and I label the nodes, this is 1 is basically this node right here. And then this one is 2. Right? And so node 2, or the capacitance on node 2, if I put a load capacitor here, it's going to be directly parallel with everything else that's on node 2. And the only thing on node 2 is the capacitance from here to the gate, CGD, for the PMOS. So that's why over here I put plus CL. Good? Any questions before we roll them? Yes?
Well, we're talking about GM2. Is it just talking about the two different transistors?
No.
GM1 and GM2.
No, here, let's pause. Let's make sure we understand that. So take a picture of this in your mind's eye, right? So if I don't know what's the deal with this thing. Anyway, all right, so if I take the picture, I just did this, right? I said, oh, this is 1 over 75K times V in. And I said it's AC, so I'm not going to worry about this being minus. And the amplifier's inverting, so the GM would be minus. Then I've got my R1, which is 75K. Then I've got my C1, which is CGSN. And then I label this node what?
Node.
And I come back over here, and I've got GM2 times V1. If I go back and I look, I want you to pay attention to this right here, GM2 times V1. If I go back, here's V1. The voltage on this is wiggling. What's another name for V1? VGS. So that VGS times GM2, which GM2 is what? Well, it's GM2 is the GM of M1. Everybody agree with that? And then that drives into the output, which would be R out N in parallel with R out P. And then shunting that, the total capacitance on the node is C2. And if I go back and I look at that, this is node 2, C2. This is AC ground. So I've got the only capacitance I have, there's the capacitance from here to here. So if I put C load, that C load will be added to the capacitance here because this side's at ground, the C load I put on's at ground, and then the other side's connected to V out. All right, before I go on, does anybody not follow this? Because when you do your reports, you need to make sure you understand how to select these values based upon F1, F2, and the 0. And the unity gain frequency. All right, so this is my simulation right here. Or I'm going to get rid of the 2 because I don't want to get confused that it's called 2 and V out. So I'll go over here. And why don't I call this V source just to be consistent in case any of you actually look at these. And then why don't I also call this VS. And now when I look at the frequency response, what is the transfer function I care about? Is it V out to V1 or is it V out to VS, and why? Yeah, it's V out to VS. My VS is changing and rolling, then my V out is going to change as well. If I go V out to V1, then I'm going to remove the pole associated with the node 1, which is F1. Well, it depends on the values. Yeah. All right, so let's hit, we calculated 23 megahertz. Let's hit roll them. And then there's our VS. It's nice 0. Oh, whoops. Let's do an AC sim. I was like, why isn't there dB there? And then I go over here to decade. Number of points, 100. Start frequency, why don't we go with 10? And then stop frequency, why don't we go with 1 gig? Excuse me. And then I hit run. And there's my input, 0 dB. Now here's my output. And then tell me where is the 0, and tell me how to identify that. It's where it starts to flatten out, right? It's rolling off. It hits the 0. The 0 says, hey, stop rolling off, start going back up. So it stops rolling off and starts going back up. So if I look, that's right around in here. What is this frequency right around in here? About 20 megahertz. What did I calculate? 23 megahertz. Let's just redo the sim a little bit, and let's start at, how about let's go with 1 kilohertz. And go to 10 gig. Hit run. So where do I see 1 pole? Right over here in about 10 kilohertz or a little bit more. Where do I see the 0? Right around in here somewhere. Where do I see the next pole? Around 1 gig. So let's calculate the others. Before I do, any questions? Well, first, any questions? Does anybody not know pole 0? When I have a pole, the pole causes the frequency response to what? Roll off. And when I have a 0, causes the frequency response to go up. So if it's rolling down and it causes it to go up, it flattens out. And if I have another 0, then it's going to start, or another pole, it's going to start rolling off. Is any of these not clear? Let's look at the phase shift. I've got a pole here. Notice the phase. We got 180 degree phase, which means the amplifier at low frequencies. What does that mean? 180 degree phase at low frequencies. What's that? Yeah, it's inverting. Then that pole causes, at roughly, whatever that is, 20 kilohertz or whatever, causes the phase to start rolling off. Where would I expect the phase to start rolling off? If the pole is at, let's just say it's at 20 kilohertz right there. Where do I expect the phase to start rolling off? Yeah, 1 decade before, or 2 kilohertz. So if I'm at 20 kilohertz, I go 1 decade earlier. Let's look at that. So I'm at, say the phase, it's 3 dB down. It's a little bit lower than that, but let's just say it's right here. And I start 1 decade earlier at 2, and that's approximately when the phase starts rolling off. When do I expect the phase to start to flatten out? About 1 decade later, or about 200 kilohertz, and that's when the phase should start flattening. Did anybody that took 220 from me remember that? When you do the frequency response, you look at the pole location, you go 1 decade earlier, means divide by 10, that's where the phase rolls off. 1 decade later, that's where the phase stops rolling off. Is that clear? That's how you do a Bode plot. Now, if I look, here's where the 0 is. But if I look at the 0, and I go 1 decade, say it's at, let's just say 30 megahertz here. If I go 1 decade earlier, that's over here. I don't see the phase shift starting to go up. I see the phase shift starting to roll down. Tell me what the deal is. The normal 0, when you have it, it's going to cause the phase shift to go back up. So why is the phase shift, and why is this such a big deal here? All right, let's pause and make sure we all follow that. You see this equation right here in the book. See how that 0 is in, well, wait, let me ask a simpler question. What's the definition of a 0 from your signals and systems?
Where the top of the transfer function goes 0.
Yeah, where it goes to 0. And so at what frequency, if I were to look at this, would I set this to, if I multiplied out the, here, let me just, I want to make sure this is clear, and I write it a little bit useful for circuit designers, but let's write it like this. Would everybody agree 1 minus F over Fz is what we have in the numerator, right? Would everybody agree that I could write this as 1 minus 2 pi F over 2 pi Fz? Would everybody agree that if it's purely sinusoidal, what is S for purely sinusoidal? J omega. What is it, S in general? Sigma plus J omega. See, this is why I feel I need to teach circuits too. All right, because you do Laplace transforms and you use the S. All right, you do this Laplace transforms in signals, right? Okay, so you've seen this, right? I'm not introducing something new, right? Okay, so then I go and I write, okay, I can write this as 1 minus S over 2 pi Fz. Everybody would agree? When does this go to 0? When S is equal to? Now, if I look in the complex plane, this is the right-hand side, and this is the left half plane. Normally, your poles and zeros, or your poles and zeros are where? They're over here, right? Where they're negative, because you have this term as positive. So in order for this to go to 0, S would be a negative number in the left half plane. But here, my S is going to be a positive number in the right half plane, or it's going to be on the border there. And so my pole, or my 0, is going to be in the right half plane. Everybody follow that? And why is that important? It doesn't influence the magnitude response, right? But for the phase shift, this transfer function in the numerator is minus tan inverse of j omega f, or I'm sorry, omega f over 2 pi fz. Whereas a normal 0, what is it? If I have a normal, yeah, it's wait, hold on, now you're scaring me. If I have the following, if I have 1 plus f over fz divided by 1 plus f over fp, and I ask you, what's the magnitude? Let's put the j's in there. What's the magnitude of that? Everybody's cool with that, right? And if I make this minus or plus, does it influence the magnitude response? No. But what is the phase shift? The phase shift of this is tan inverse of f over fz minus tan inverse of f over fp, right? But what if I do this? What if I make this minus f? Doesn't this become minus f and this become minus here? So isn't the phase shift in the same way as the pole? That's bad, right? Why? It's bad because now I go back and I look at the simulation here and I say, hey, instead of the phase shift going back up to where it was at low frequencies, it's rolling off. So that right half plane 0 has a phase shift which is in the same direction as the pole. That's why it's such a big deal. Now, I'm going to pause and I want you, this is a good job interview question. I want you to tell me, intuitively explain that. Intuitively tell me why you're getting that phase shift increasing and why it's bad. And the answer is the following. When you look at your amplifier, and you have low frequencies. This goes up, this goes down. This goes down, this goes up. Everybody would agree, right? When I have high frequencies, this capacitor starts to act like a short. And so this signal goes high, and it feeds through the capacitor and has this signal go high. In other words, the inverting behavior of the amplifier is lost. So you're going to get positive feedback because the signal that can then come back and feed back to the input because you're shorting the input and output. So this capacitor, which we don't see in the Miller's there, goes straight through and feeds the signal through and bypasses the inverting action of the low frequency amplifier. Makes the phase shift go towards 0. Okay? And I'm going to pause on that too because I want to make sure you follow why that is. And then we need to change gears and talk about, so I'm not going to calculate these, you probably have done it already. But you see the phase shift is starting to go towards 0? See that? Starting to go towards 0? So let's pause. And I want to ask, why is that important? Why is it important to avoid where the phase shift is changed to 180 degrees? Okay, so we're going to do a real quick controls. Anybody taking controls? All right, so I want to do, you're probably using G and H. I'm going to use AOL and beta, but they're the same thing. You have, here's your input we'll call VN, and then here's the subtractor, your feedback, your negative feedback. Here's your forward gain, which I'll call AOL, open loop gain. Here's your output, and here's your feedback factor, beta. Everybody would agree? And what do you call these in control? So everybody remembers in control that's G and this is H. So you would all agree that this right here is V out times beta, or V out times H. You would agree this term right here is V in minus V out times beta. And then you would agree V out is equal to AOL times V in minus V out times beta. Yay? And if I solve for this, if I get all the like terms together, I get V out times 1 plus beta AOL equals AOL times V in, or V out over V in equals AOL divided by 1 plus beta AOL. Anybody seen that before? Okay, so when we're unstable, when beta times AOL is equal to minus 1. What is the magnitude of beta times AOL then? 1. What is the phase shift of beta times AOL? What is it? Plus or minus 180, it's minus. Right? Tan inverse of minus 1 over 0, tan inverse of minus infinity. Anybody agree with that? So we want to avoid where this term, where the phase shift is 180 and the gain is 1. Now, in a real circuit, the most, without an amplifier and a feedback, the most signal that you could send back is all of the output, and that would be where beta's 1. And a simple example of a circuit that has a feedback factor of 1 is this. Everybody see that? And so when I look, I don't want to change by 180 degrees like I saw in my simulation, because if I get to where my gain, it's a little harder with a one transistor with a simple amplifier, if I get to where my gain, which is here, is 0, close to where the phase shift is 1, then I'm going to be unstable. Does everybody follow that? Okay, so let's go. Are there any questions on the frequency? I'm going to cover this this stuff again later, but I want to talk about the gain of cascode amplifiers. All right, did you get as close as what I was getting, the 23 megahertz and all that when you did it? So it wasn't that bad, was it? You just felt like you couldn't use the equations, the F1, F2, and FZ? Why? Because I need to feel pain.
Yeah.
All right, well, that's the way to do it, is to use those equations. Okay, so let's do cascode amplifier. And then we'll do our grade booster. And cascode amplifier is sometimes called the Miller killer. And you'll see why. All right, you'll understand why in a moment. So this is V bias 1, V bias 2, V bias, and everybody understands the bias voltages, right? Yeah, I won't do frequency response for a minute. If we have time, we will. Then I want this bottom one to sink the amount of current that's needed. And so I'm just going to calculate the gains. So if I were doing frequency response, this would be node 2, and this would be node 1. Okay? All right, so what is the VGS of this transistor? Don't all scream it at once for AC. What is the VGS of that transistor? VN. Anybody not see that? So what's the AC current that flows there? Don't forget this. It's transistor. What's this AC voltage? My students in circuits 2 do not like it. There aren't previous videos to watch.
Wow.
So if that's 0, and we say the current flowing in here has got to be roughly what? Would everybody agree with that? What is that voltage right there? AC circuit. This is 0. What is that AC voltage? Correct, minus VN. Because the VGS here is GM times the gate voltage, which is 0, minus VN. And so doesn't that voltage have to be minus VN? Everybody see that? So if I ask, what's the gain from here to here? -1. Explain to me, just based upon that, and I'll draw Miller capacitance in there. This we'll call CGD. Why this is called the Miller killer. Because the gain on that cross-that capacitance is only -1. It isolates the input from the output in the high gain, so that I don't get the Miller capacitance, and that's CM times 1 plus A. Everybody see that? But we still need to calculate what the gain is to right here. So you told me the current that's flowing here is GM V in. What is the resistance I see looking up there?
Eight in parallel with.
What's R out cascode P, right? And what's the impedance I see looking down there?
Cascode.
And so I ask, what is V out over V in? And it is minus GM times R out cascode P in parallel with R out cascode N, which is going to be considerably larger than what we just had in that circuit that we showed a moment ago. We could calculate and show the R out cascodes are in the table in chapter 20. What I'm going to do instead is I'm going to do a simulation, but before I do that, are there any questions? So I get my gain, I'm going to get a huge gain. However, I don't have the Miller effect. So what do you think the issue, or what do you think about cascodes? Super useful. Right? Because if you get high gain and you don't have the low limited frequency response. Okay, so wait a sec. If I put a capacitance from here to here, call it CC, does that get rid of that Miller capacitance? So if I put a 1 picofarad between here and here, would I still have the Miller capacitance here? Yes. Because I still have a big gain on one side of the capacitor and a small gain on the other. Any questions?
So that one capacitor, that CGD, is that still there? Or?
The one? Yeah, that's the capacitance of that device. I want to do one more question or one more problem. I think that was your quiz. I want to do that one real quick from last time. Actually, let me look at the quiz today to see what it is. Oh, yep, CMOS. No transistors. You got a question with no transistors.
Be a voltage divider, right?
Nope, but let's do that quiz last time. Are there any questions on this cascode? Now, the reason I want to do the quiz is because I could include the R out here, and 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 we could spend a lot of time in algebra doing math. This is the way when you're working in industry that they say, oh, this is what the gain is. All right, but I want to do one with the R outs, but I want to do the one you did in your quiz last time, which I think looks something like the following. It was, you had your bias, and I'm just going to draw the AC circuit. And this was VS, and this is IS, and this was V out. And what was the problem? It was, what is the input impedance?
Correct.
What was the
DC.
input current? Well, the DC current's easy, right? What was the answer? 20 microamps, DC. Let's do the AC. So, would everybody agree that this voltage here is minus VS? Would you agree this current here is GM times VGS, or GM times 0 minus VS? Would you then agree that if I define my VS over IS as my input impedance, that I've got the following? So if I just, this is IS. If I define that,
That's negative, right?
minus IS, yeah, which is ID. And I define that, I get minus 1 over minus GM, or 1 over GM. That's the answer I was looking for, but let's make it a little more complicated, shall we? Did anybody get that? All right, let's make it a little more complicated, and I'm going to include the output resistances in, and we'll do it that way. So would everybody be okay if I wrote this as R out P? Then here I wrote a current source, which is, this is my gate, it's at AC ground. This is my source, it's at V source. Then I have this going in, this is GM VGS. Then I've got my R out P here. And this is my IS, and I'll just write it like that. Anybody agree with that?
Yeah.
Anybody understand what I've drawn?
That's RLN, right?
Or yeah, R out in. That's just testing you. Okay, any questions on that? If I said don't assume 1 over GM is much less than R out, this is the way you would do it. What do I look and realize looking at this circuit? I want to minimize the pain in my life. Too late, I took your class. Tell me something I can use to minimize the pain.
IS equals VM.
Correct. IS, and this voltage is?
Yeah.
RON divided by ROP.
What? It's just this current goes in and it comes out here to ground.
Oh, 0 minus IS times ROP.
Yeah. It'd be this voltage is IS times ROP minus this voltage 0 divided by ROP is IS. Tell me what to do next. So would everybody agree the current going in is IS, and that's equal to, let's say, oops, I should finish this, VGS. And would everybody agree VGS is minus VS? So this side is VS, this side is IS times ROP. IS goes in, that's minus GM times minus VS. That's this current. Anybody agree with that? It's minus because this one's going in and this one's going in. Yay or nay? Proceed or stop? Clayton. Okay, so let me do it again. Would you agree the current going into this node is IS? Would you agree that one of the currents going into this node is GM VGS? So I would write plus GM VGS, but isn't VGS the gate voltage minus the source voltage? That isn't the source voltage VS. So wouldn't that be minus VS? And then let's see, which way do you want this current to go? Why don't we make it going in as well? And that current would be IS times R out P minus VS all over R out P, and that's equal to 0. I did a KCL at this node. Yay or nay? Okay, so the water's flowing through, right? Water splits through these two pipes. Then it comes out this pipe and goes to the ground. So isn't IS going here? Doesn't it have to come out here? Yeah, this here, let me not be lazy. So then it does this, circuitol, circuit. All right, now someone's going to say my notes look like spaghetti. What's that? Oh, you did. See, I knew it. I was ready. Okay, so what do I do now? Just solve, right? And what am I after? Well, what am I after for the input impedance? No. VS over IS. Yeah? Okay, so let me split everything up and I'll put the VS's. So why don't I do this? Times R out P, cancel, times R out P. And so I'll move the VS's over here and I get VS times 1 plus GMR out P. And then over here I have IS times,
It's supposed to be RON.
what did I do? Oh yeah, sorry.
And then the bottom one.
No, wait, no, the.
Oh yeah, you're right. That's ROP. And this is RON, so this would be RON. This would be RON. And so that would be 1 plus GMRON. And then IS would be times RON plus 1, or plus RON. Looking good? Oh wait, did I mess up again?
Hey, Doodle.
No! How about that? Does that take care of it? All right, and then I get VS over IS is equal to RON plus ROP divided by 1 plus GM times RON. And I'm going to divide the top and bottom by RON. Let me think if I can get an easier way of doing that. And that's divided by 1 over RON plus GM. And that ends up giving me approximately 2 over GM. And so this is the answer. If you do it precisely, it's off by a factor of 2 from just estimating 1 over GM going in, because of the output resistance of the transistor. Did anybody get 2 over GM? You did? Did you get full credit? Anybody else get 2 over GM? That's not what I would have got, but oh well. Now let me pause and show you where that similar calculation is in the book. But I want to show you for the cascode structure, which is a little bit more complicated. Before I do that, any questions? And I want to cover one more thing real quick, which is, now do I need to cover the biasing? The DC biasing for the cascode? Well, I know I've done it before, but it doesn't mean anything. It's the truth. All right, let me pull up. If you look here, see this circuit right here? Where it's, I'm injecting a current into M2 here. And then I ask, in this case, what is the input resistance? And what is the gain and all that? And then you can see the derivations down there of V out equals I in times minus R out cascode N in parallel with minus R out cascode P. Same exact result. And what kind of amplifier is that called again? No. Why is it called a transimpedance amplifier? Outputs voltage, inputs current, so the gain is V over I. V over I is resistance, so it's called a transimpedance or transresistance amplifier. Any questions? We ready for the quiz?
No.
What? Yeah, open book. And I made sure that I put that this time.
Open book.